All right, can we hear me? Fabulous. All right. So, ladies and gentlemen, welcome to this session. You are in the right place for sure. We're going to be working here with Greg Benedis-Grab, and I'm going to go ahead and give you just a little information about him before we get going. Greg's been teaching science, engineering, and technology for over 18 years. He received the Presidential Award for Excellence in Science and Mathematics Teaching and was a finalist for the Shell Science Teaching Award. Greg has presented on science, technology, and innovation at national conferences and leads teacher workshops globally. He's currently the technology coordinator for the Packer Collegiate Institute in New York. He's also an adjunct assistant professor at Bank Street College Graduate School of Education and Hunter College. And with that being said, I've also spent some time working with Greg myself, and he's fabulous, so you're in for a show. Here we go, ladies and gentlemen.
Great. Thanks a lot, Chris. I'm excited to be with everyone here at the Education on Air event. It's a very exciting weekend. I see there's a lot of exciting events going on. I'm definitely going to be checking out some myself. But today I want to talk to you about using digital tools for STEM. And to start off my talk, I just want to think a little bit about, before we start talking about the digital tools, I want to think a little bit about what STEM means. And by the way, as he said, I'm Greg Benedis-Grab. So, and I think so you can make comments on the event, and Chris will try to keep an eye out for questions for you, so feel free to write in any questions. So I want to think a little bit about what STEM means. I think there's a lot of confusion about STEM, and it's become a hot topic. And so I kind of want to question, you know, some people, anything that's science, technology, engineering, or mathematics, they throw it into the STEM, into kind of the STEM circle. Some people look for some intersection between those four fields. I'm going to define STEM today and try to show how it can be powerful in the classroom. So I'm going to say that STEM is about solving real-world challenges from the personal level to the global scale. And what set of skills and understandings could be more important to our students, to the generation of leaders, workers, and citizens who are preparing for the future in our classroom? So I think we really need to think about what STEM is before we start teaching it. And today I want to look at what I consider three essential elements of STEM. The first is data, the second is collaboration, and the third is design. And so with those three different perspectives, let's look a little bit at what that can look like in the classroom, and how we can kind of rethink STEM to make our classrooms a more powerful, engaging place for students. And so let me switch over to my slides here. Oh, was I on my slide my whole time there, Chris?
No, sir, I was watching you.
Okay, excellent. So let me go over to the slides here. And here we have data. So I first want to talk about this device here. This is a motion sensor. And a motion, I've done a lot of work with motion sensors. What they do in the classroom is they let students see the data of motion directly. It can track an object. It can give you information about movement of an object. And what I did with a group of fifth graders is had them use this device to actually measure their own motion. And so they would stand in front of this motion detector and make graphs. Here, let me show you an example of what one would look like. So here on the x-axis, you see the time passing, and on the y-axis is the position, or your distance away from the sensor. And I would have students, you know, I would give them graphs and try to have them replicate it. They would make their own graphs. And I think what this device does is it lets students get a new perspective on motion. And I found that the fifth graders had a deeper understanding of motion and complicated concepts such as acceleration, reference point. All of these things became more powerful because of their access to the data in this new and different way. And so I think it's important that we think about using digital tools to kind of bring data alive in the classroom. And if you really want to bring data alive, you have to think about, well, what data do students care the most about? And you know, for those of us who've worked with middle school students, or actually a wide range of students, they care the most about themselves. And so what I did was I handed these same students a pedometer, one just like this, and they started to keep track of their own steps over the course of a week. And in this activity, they could see how different activities changed the number of steps they use. They could relate this to health and wellness. They could relate it to a lot of things. They could get deeper into thinking about motion and Newton. Hold on one second. And so, hold on one second.
You okay, sir?
Sorry about that. And so by using these powerful devices, they could really control, you know, answer their own questions about the world and really think more deeply about the data that they're using. And not only did they get really involved in this data, they could really deal with messy data. The data they got from these devices, sometimes it wasn't so accurate. Sometimes they moved the device around and got steps that they didn't even make, or sometimes they leave the device at home and forget to collect the data. And so by dealing with this real data, they gained all these skills of how to clean data, how to analyze it, and how to look at it more deeply. So I think, you know, this is just one example, but we really need to think about how we involve students in data and make them part of this process. Another thing I wanted to share was that data is more than just numbers. It's not just, you know, numbers that you collect. It could be images, it could be video, and in fact, let me just switch over back to myself here. I actually did an experiment with some students where they were, you know, experimenting on plants. They were collecting some data, trying to answer their own questions about the plants. And one of the things they came to was they said, you know, we love all the information we're collecting in school, but we don't know what's going on with the plants outside of school. We don't know what they're doing at night. And so we got this idea as a group to videotape. In fact, we did a time-lapse photography project with the students, collected this data over the course of the day, and I just want to show you an example of what this looks like, because you know, using these technological tools can allow you to collect all different kinds of information here. Let's see here. Just waiting for this video to queue up. For some reason, I'm not getting the red button. Here we go. Well, hopefully this will work in a second. Let me see here. Let me bring it out of this and then go back in. One of the things, you know, you learn using technologies, you have to be patient with the way the technology is working here. And if we can't get this to work, it's okay. I got it working earlier today. But basically, what you would have seen in the video is the plants moving with the light. And so by collecting this additional data, the students were able to think about things like phototropism and advance things and really kind of consider all of these aspects of plant growth. And really, ultimately, they answered their own question. They wanted to know something that went beyond what was happening in the school day. And using these digital tools, they were able to kind of take this STEM to a deeper level. And so I think it's really important. And data isn't just the data that students collect. There's a lot of great examples of using published data, data that's published by the government, by various organizations. And so you can really take data to the next level in your classroom by thinking creatively and really getting students deep into the data. But not only do we want them thinking deeply about the data, we also want them to be thinking about how to communicate the data and share the data. And so I'm going to put up this slide here. This is I don't know if you guys recognize this. Was sometimes referred to as the ghost map. It's what Dr. John Snow in England used to kind of unravel the mystery of cholera. And what he did, you'll see there's a bunch of lines on the graph. Those represent all the people who died in this neighborhood of London. And using that information, and based on where people were located who died, he was able to prove that the disease was waterborne, that it was coming from this particular well that is in the center of the slide. And that just kind of speaks to the power of data visualization and how important. And I think it's really important to get children of all ages involved in thinking about data visualization and how you can show information in new ways. And give your students the opportunity to show their information any way that they think they can communicate it effectively. So I just wanted to put that up there to kind of think about this idea of data visualization and students showing their ideas. So, I think data is a key element of STEM, and I think if we're going to take STEM to the next level in the classroom, we really need to think about this use of data. And so that's the first thing I wanted to address. The second piece that I want to address is collaboration. And collaboration is a key element of all of those fields: science, engineering, technology, and mathematics. And I think it's a key skill for students of all levels. But I want to kind of build off of our work with the data. One of the things that I think is really powerful in STEM is focusing on the collaboration of data. And so I want to show you a couple of examples that show what I mean about collaborating and sharing with data, because I think this is an area that I haven't seen a lot of work on, especially in the K-12 realm, of really letting students share that data. The first example I'm going to show you takes us all the way back to the world of ancient Greece. And in ancient Greece, let's see, one second, I'm seeing the collaboration screen. Oh, here it is. Okay, so in ancient Greece, in Alexandria, you probably know that Alexandria was the home of the greatest library in the world. And the person who ran that library was named Aristophanes. And he was a scientist, he was a scholar, he was a lot of things, as a lot of the ancient Greeks were. But he came across this account in the library, he was reading about it, about a temple in Scene. And you can see where Scene is, it's one of the dots on the map there. The account was that I think in the month of March, at the noonday, during the noonday sun, the columns of the temple cast no shadow. And this really surprised Aristophanes, because he went out and he checked the shadow on the temples in Alexandria on that same day at that same time, and there was a shadow. And from this information, he was able to use the angle of the sun, calculate the angle of the sun. And then he actually got the distance between those cities. He actually had to pay someone to walk and count the steps from Alexandria to Scene, if you can imagine. And then using all that information, he got one of a really accurate measurement of the circumference of the Earth. And the reason I'm telling you this whole long story is because at the Stevens Institute of Technology, they created a project where students could recreate this, sharing this data in a shared global environment. And here I'm just showing you a couple data points that were collected. One is from France. You'll see students in France at the Collège Antonin Perbosque got the angle of the sun on March 23rd. And they got the latitudes from Google Earth, so they didn't do it quite the same as Aristophanes. And then other students in India collected the angle of the sun and the latitude, and from that information, using the same exact formula that Aristophanes used, they were able to calculate the circumference of the Earth to an incredibly accurate value. And so you can see how sharing data globally or regionally can make a huge difference in not only in making STEM education more exciting and alive, but in really making it more informative and really showing students how data shared in this way can make a huge difference in our scientific understanding, in our engineering accomplishments. Let me show you one other example. This is also from the Stevens Institute of Technology. This is called the International Boiling Point Project. And in this project, again, students are sharing information globally, putting information out there online. And what I find interesting about this is usually in school, you're told about boiling. You're told about what factors are important. But in this experiment, students just aren't told anything. They're told, measure the boiling point of water and tell us all the factors that were going on in your experiment. And then you can take that data, that large sample of data, and you can plot it on a graph. So let's just look here. In this graph, you can see it's volume versus boiling point. It's scattered all over the place, and so there's clearly volume is not an important variable. So students aren't being told that volume is not an important variable. They're discovering it by sharing information with other students in other places, and I think that's a really powerful thing. Here is kind of the big lesson from it, is that elevation does make a difference. You can see there's a correlation in the graph, and that correlation is what's important. So the information isn't what the textbook says. The information is the data collected by the students, put together. They can see on the graph that elevation makes a difference, and then you can get deeper. Well, why does elevation make a difference? You can have those discussions, but it comes from a point of student data, which I think is particularly important. I wanted to come back to that example of growing plants, because I think that's another example where shared data is so powerful. When I first started teaching science and having students develop experiments and answer their own questions, I would have them work in small groups and collect some data and draw some conclusions. And usually the data wasn't that valuable because it was there were a lot of errors involved. It was hard for the students. I mean, the process was great. The students, constructed the questions, and they really worked hard, but not that much came out of the results of the experiment. But as I found ways for students to use something like a Google spreadsheet or some other way to share data, that large quantity of data made it so much more powerful. And so suddenly even the errors in the data started to kind of fall out, and kids could still see patterns in the data. And here, just to show you what that might look like, here's an experiment that I did with a group of middle school students where they just entered their data into a huge spreadsheet, and then when they drew their conclusions at the end, they could draw from all of the data. And it made them accountable to each other. It made them really realize the importance of learning as a group. And again, as I said, those trends, those patterns became that much more powerful because we had a bigger set of data. And I do want to tell you one story about that. I had this one student named David who was looking at all this data, and he was looking at the control plants and the experiment plants. And he said, every time we do an experiment, the plants do worse. They produce less seeds. They grow less tall. Sometimes they grow taller, but then they die. It seems like any time we're changing the variables, it's actually making the plants worse. It seems like the control plants are the best. And he was inspired by that to say, well, I bet I could grow the plants better. And he thought about different ways of doing it. He thought about all these variables, and what he ended up coming up with is, instead of changing the amount of fertilizer, instead of changing the amount of space, instead of changing the water, he decided to have the plants share root space. And so he gave them the same amount of space, but the roots could intertangle with each other. And his experiment ended up producing some of the some of the highest, the tallest plants, the most seed production. They were they were by all our definitions the most successful plants. And the whole class was shocked that he was able to do this. And actually, as I started to do research on it, I realized that biologists in peer-reviewed journals were doing similar experiments. And so I think the message here is that if we let students kind of explore the data, get involved in the collaboration, and really pursue their own questions, they can do amazing things. And we have to make sure we're not holding them back, that we're giving them the full opportunity to kind of explore the world. And just one other thing about collaboration that I wanted to show you. I do a lot, oh sorry Chris, I do a lot with peer review and sharing of information, and I think letting students review each other's experimental ideas, letting students review each other's experimental results, and really making the classroom into a sharing community is a key part of STEM education. It's really important that the whole class is working together to make this happen. And so that's just something important that I think we need to bring to the table in our STEM work. So that's the second part, the collaboration piece, and I don't think I can stress that enough, especially with where these fields are going. I mean, you look at the Large Hadron Collider, and you have teams of 80 or 90 people working together, engineers, scientists, mathematicians, people from all these fields having to work together to solve problems. And so we need to make collaboration a part of that. The last piece that I wanted to stress was design. And I think this is where people started to change the acronym from STEM to STEAM. And I'm not sure how successful it is just adding more letters to the acronym. I don't know if that always gets accomplished, what needs to be accomplished. But I think that artistic piece, that human piece, is so important to STEM-type thinking. And I want to show a couple of examples of where I think you can incorporate design into your classroom and how that can really bring all of this alive. Because as I said at the beginning, this is really about solving problems, and our students can solve problems really well. They are engaged by problems, and they have amazingly creative ideas. And so I just want to kind of think about how can we put this in the classroom. So one thing you can do, which is great in science and in all of these fields, is incorporate something like the Arduino. I don't know how many of you have used the Arduino. It's a great, cheap controller that lets you do computer programming. It lets you do some circuit board design. It teaches you a lot about electronics. But what's really amazing about it is that it's cheap and simple, and there's tons of stuff online that students can build off of. And so I've done some work with this in middle school, just having students kind of try to figure it out, go through the help documentation, try to play around with it and get it working. And once they get comfortable with it, you can take them through the design process and really think either theoretically what they could do with it, or they could actually start to prototype some of their answers. And this is just an example of the design process on the IDEO website. It starts with a challenge, a problem you want to solve. A key piece is number 3, the ideation, when they really try to come up with as many ideas, and this, the collaboration is so important there. And then finally, there needs to be some sort of putting it into action, and then reiterating and getting it working and evolving it from there. And just to give you a quick example, I did this work with some middle school students. They were playing around with the Arduinos, and so what they did was there was one group who said the problem is that, and this happened to be during the winter, and they said, the problem is that kids are getting sick all the time. We have 5 people out of class. How can we solve this? And they were starting to think about how germs spread. I think we had done a unit on disease earlier in the year. And so they used this design process to kind of think about how they could solve that problem with something like an Arduino. And what they came up with was a motion-activated door. And what was so great about that is they could kind of think through the process of how they would build that, but they were also able to make a prototype of a model cardboard door that could open and close with a servo motor. And they could really think about all of the issues that would go into that. What would trigger it opening, and how would that work for classes, and how would that work during a fire drill, and all of the different things that we want our students thinking about as they try to design solutions for the world. That can happen in our classrooms. And I think one of the big takeaways I'd like for you from this talk is just that let's not limit the kids. Let's open things up. If we want them to be the problem solvers, we need to put them in those situations where they can solve the problems. Here's one other example. This actually also is from the Stevens Institute of Technology. They developed a very interesting program with Lego robots. You've probably seen a lot of things using Lego robots. I think it's one of the big STEM go-to activities. Well, they took those robots and they stuck them in the water. And so essentially you have a submersible, which just so happened it's all over the news these days, oil spills and all of these different things going on. Submersibles are getting so big, but the submersible piece kind of adds that creative element to it. They have to, there's a series of challenges. First they have to get it to go in a straight line. Then they have to think about making a figure eight. They have to deal with the gear ratios to get the speed of the propeller right. They have to figure out the buoyancy, the fluid dynamics, all of these things, these very complicated things. But they're attacking it in a real-world problem, and then you can just throw challenges. You have to, you have to protect us from the oil spill. Or you have to get these things off the surface of the ocean. And these kinds of projects that let students face challenges and overcome them, I think, are such an important part of getting them ready for this 21st century that's ahead of us. And so just to kind of recap, I think it's really important that we think about data, collaboration, and design in how we pursue STEM education. And if we are going to teach students how to solve problems from a personal to the global scale, we need to give them practice doing it in the classroom. And with the power of digital tools, we can make that happen in new and exciting ways. And so I think we have about 1 minute left. Sorry about that, Chris, for questions.
No, it's no problem. There are a couple of questions.
Right.
There are some folks who are having some problems and they just having a black screen, and I'm not sure how to help with that, but at least we can try to answer some of these questions. One of the questions is, what would you recommend to educators and how to STEAMify themselves before equipping, enriching, and empowering the school community, especially the children, to become productive global leaders? So what are my first steps to just get started, basically?
I think ultimately the first step always starts with the kids or the students, and really thinking about what are they interested in, what excites them, and then that's going to help you figure out which problems they want to solve. And there's so many different ways to bring problem solving and STEM into your classroom. I would suggest starting with what's interesting to the kids and what's really going to get them excited about it. And another key element of it is that play or exploration phase. And so thinking, especially if you don't have a lot of that play and exploration in your classroom where students can kind of think of these kinds of challenges and problems, then trying to incorporate that in will give them that kind of foundation so that they can start to attack these kinds of problems.
Yeah, absolutely. And then another question was, can you make some of the resources and samples you've mentioned publicly available?
Sure. I'll post some links after that. I guess I'll figure out how to do that. But yeah, I can definitely post. A number of these things are already posted online, so I'll just pull together some of the links.
That's fantastic.
Everybody.
All right, well, ladies and gentlemen, thank you very much. I think we're just about out of time. I know that Greg can make himself available to you if you have other questions or things you'd like to work with him about or talk with him about. But thank you very much for being here. We certainly appreciate it, and we're looking forward to the next sessions.
Thanks a lot, Chris. Okay, thank you, everybody. It was great. Great time.